In this video, I'm going to talk about classification, and first I'll do a live coding example, how we solve a classification problem with the decision tree. Then we're going to look into a bit more details how classification trees work. And the great news here is you know almost everything about trees already. And there is only a minor difference, important but minor difference between regression trees and classification trees. So switching between those two would be pretty easy. And same applies to random forests. Random forests for regression and random forests for classification are actually even more similar. Their logic is almost exactly the same, except that they use different underlying trees. So in this example, we're going to build a tree, only instead of doing a regression problem where we were predicting a continuous variable such as price, we will be predicting different classes of things. So let's take a look at a particular example. First, I'm going to do a few imports. Matplotlib pyplot splt, import numpy as np, import pandas as pd. So I'll add more things as I need them, and I'm going to import a data set. So instead of downloading a data set from the internet, we are going to import one from scikit-learn that comes with a few data sets, few useful data sets. In this case, it's called iris. So I'm going to say iris equals load iris. And what this returns is an object, actually a dictionary, with a number of keys that includes the actual data, feature names, and so on. So let's take a look at feature names first. First, let's take a look at feature names. And we see there are four features or four inputs in our data. Sepal length, sepal width, petal length, and petal width. That describes a flower, one of the three types. And the types that we have are setosa, versicolor, and virginica. These are the three classes into which we need to classify the flowers based on their characteristics. The data itself is stored in a parameter called data. That is just a matrix. Each column corresponds to the features as they described in the feature names, which are right here. So the first column would be sepal length in centimeters. The second column would be the sepal width, and so on and so forth. So what we actually can do, since this data set comes as a numpy array as an input variables, and we used to using the pandas data frame as inputs, we can simply create a data frame from the numpy array in a very easy way. So we're going to create a new data frame. The first parameter of data frame is called data, and we're actually going to pass this data matrix, and we also need to assign columns. If we don't, we'll simply get these kind of index numbers 0, 1, 2, 3. But since we know what our feature names are called appropriately, we can simply assign columns iris feature names. And this will create this nicely formatted data frame. Same data, but with the nicely called column names. So let's save it, and let's call it traditionally as CSVDF. This gives us all the data that we need. And we actually don't need to do any pre-processing here because we already get numerical data. So there are no categories, no dates, so it's a very simple and easy to use data set. And the second column of value we have is what we're trying to predict. In this case, that is a target, iris.target. A target is just an array of zeros and ones and twos. Each of them corresponds to a class. So class 0 would match setosa, class 1 would match versicolor, and so on. In fact, we can convert targets numbers into class names by indexing appropriately using the target names as an index. So we can look up for every index, we can look up the actual name in this array. So that could be quite convenient. Our target is essentially our y, is that what we're trying to predict. So I'll just assign it to y. And our x, or array of features, would be our CSVDF in its entirety. Okay, so now we can check their shapes. And we got 150 samples total, 4 input features, so we know what these are. Their length and width of sepal and petals, respectively, and we have 150 labels. So following our process is exactly the same. We're going to shuffle the dataset and split it into 2 datasets, train and test. We're going to train our tree, and then we're going to validate results on the test set. And that's where shuffling is quite important, because if we look at the labels y, they all sorted. So all the first 50 rows are type 0, then type 1, and type 2. So if we'll simply split the dataset as 70-30, what we'll end up getting is labels 0s and 1s will end up in a train set, while the remainder will be in a test set. So we'll never be able to actually train an appropriate model, because during training our model would never even know that class 2 exists. So that's why shuffling, generally speaking, is a very good idea when you before splitting the data sets, to make sure such strange situations won't happen. So that's where shuffling comes in play really well. So I'll do from scikit-learn import model selection, import train test split. I'll just use the standard function for now. X train, X test, Y train, Y test, train test split. I get X, Y test size equals 0.2. We can now check the sizes to make sure we got what we expect. Okay, everything adds up. 120 samples are in train set and 30 samples are in test set. Also, let's check our Y test to make sure we got the values of both kinds. So as you can see, the result of shuffling, which train test split does by default, we ended up with values of all 3 kinds. So this is good. Let's import our tree from scikit-learn.tree import decision tree classifier. Since we're now solving a classification problem, we will need a classifier. We're not going to regularize the tree in any way yet, and we can train it. So inputs are X and Y. Actually, that would be the entire data set, which is not what we want. We want X train and Y train. So now we can print metrics and see how our accuracy is doing. So first I can do DT score on a train set. And it's a very simple data set, and we did not constrain the tree. Think for a second what we expect our square to be in this case. Make a guess. So if you remember our previous class, when we talked about unconstrained trees, tree will try to accommodate every single sample, and so eventually we'll end up most likely with a single sample in each leaf node. So if we're going to test the tree on the same train set, we'll essentially find those very leaf nodes for every input, and we'll make a perfect prediction, which is just equals to the sample itself. So in this case, our score will be perfect, 1.0. Now, of course, that doesn't mean much. to actually understand how well or poorly we're doing, we need to test the tree on the test set. And we can simply use the score function to run the predictions and calculate R² in one call and see what the result is. So all that the score does, and most of you have implemented it already, it calls predict for the X test or for any input here. So I end up with and produces Y predictions, and then calculates R² for Y predictions and Y test that we're passing. And Y test are the actual values. So the score function does this for us automatically. Well, you can do it by hand to make it more clearly. So on the test set, our accuracy is a bit lower. And actually, one correction. So this score, since it's a classifier, it's not really R². So this R² would be in the case of the regressor. For a classifier, we're actually testing the actual accuracy, which is means of the given samples. In this case, in the test set, we had 20 or 30, as you can remember from here, 30 samples. We guessed correctly or predicted correctly 93%. So we can actually validate this by hand to make sure that makes sense. So we'll run a prediction for our X test. So these are our predictions. Now we're going to compare them to the actual expected values, which are Y test. So with NumPy, I can simply write this, and this will what we'll do. It will compare values one element at a time, and we'll produce an array that says which elements match. So as you can see, most of the elements match. We get trues almost everywhere except for a couple. Also, true is interpreted as 1 and false as 0. So if I simply sum this up, I will end up with the number of predictions that we guessed correctly. It's 28 out of total, and I can use ypred.shape0, which will give me the number of samples that we have, which is 30. And this will give us a 93% accuracy. So we correctly predicted 28 out of 30 samples. So it's a pretty good result. We're overfitting a little bit on the train set, but the data set is pretty clean, if you will. So we have a clear separation between different classes, more or less, and we end up predicting 93% of our values correctly. So that's how the tree works, and we can use another additional helpful function. Since we have 3 classes, 93% prediction, just a single number, isn't really telling us much, because it's good to know that we're pretty accurate, but what if we're making a really bad mistake for one class and we're doing great for the other 2 classes? So that would be good to know. So for classification, a very useful function is a metric is called confusion matrix. So from sklearn metrics, I'm going to import a function called confusion matrix. And confusion matrix takes 2 parameters. First is the actuals, in our case is Y test, and the second is predicted values. And it's going to print the matrix, where the rows are the actual values and the columns is what we predicted. So, which means the class 0 has the total of 6 points in our test set, and we correctly predicted it as class 0, and we have no other predictions for this class, which means it's a perfect result. For class 1, we have the total of 14 samples, 13 plus 1, and we correctly predicted it only 13 times. So this is the column number 1. And of this class 1, the actuals, we have one prediction that actually put one sample into class 2. So we misclassified one sample from class 1, and we also misclassified one sample from class 2. So class 2 would be 9 out of 10 correctly and 1 out of 10 incorrectly. So we flipped 2 classes, we flipped 2 samples between 2 classes. So basically it's kind of one error, but it's still a pretty good result. So now let's take a look at what the tree looks like. So now we'll use our library. CSC665, import metrics, and metrics should have a visualized tree, which takes the tree and feature names. So our tree is DT, figure size we'll keep by default, and feature names would be, we actually have the value called feature names in our data set. And I need to use matplotlib inline directive so it displays graphs right away. There you go. This is a fully unconstrained tree that goes all the way to the bottom, where we'll end up with a single sample in each node. The tree looks a little bit different from the regression tree. We still have a split condition. That's a common characteristic of all trees, so that doesn't change. And we also have how many samples we have in each node. We're starting with 120 samples total as our input in our training set, and then we start splitting using this condition. The value is a little bit different, and what the value does here, instead of calculating an average, which would make sense, because the average of between different classes actually doesn't mean anything, unlike a continuous variable, here it displays all the values from different classes that ended up in this node. In other words, we have 44 samples of the class 0, 36 samples of class 1, and 40 samples of class 2. And the way the tree works is once we reach a node, let's say we only have a root node and nothing else, right? What prediction will we make here? We will make a prediction, if we have to predict one class, of the class that has the majority. So in other words, since the class 0 has 44 samples, we consider this class to kind of win this vote. So our prediction for this super basic single node tree would be a class 0. Now, of course, it's not very useful because it looks like pretty random. All classes are almost uniformly distributed, and the only reason why we have different values is because our train test split simply divided data set this way. So what the tree is trying to do as it trains itself is to split these values by using the inputs, which are, again, features that are called sepal length, sepal width, and petal length, petal width, to split these subsets into pure sets. So as you can see, if we use petal width condition less or equals 0.8, then in the left node, we immediately end up with a pure set, which has samples of only one class, the class 0, 44 samples. And so if we pass a new input and it passes this condition and goes to the left, then we can make a very, very confident prediction that the class of this input should be class 0. And if we go to the right node, in other words, if petal width is more than 0.8, we'll now end up with a node with two classes that are mixed together. And so subsequent splits will separate those two classes as well, and so we'll end up with a pretty pure sets at the end of our tree. So in fact, we're reaching a pretty good quality of the tree by the third, or actually second level. So, and other levels are probably begin to overfit a little bit. So even at these two levels, we already can make a very, very confident prediction that this node would be the class 2, and this node would be class 1, with only a few class 2s mixed in there. So that's how we make predictions. We simply look at the total values of all classes that we have in this node, find the most frequent one, the highest one, the majority one, and that's what our prediction is. And to do this split, we need to calculate an error metric. In the regression case, we used a mean squared error, but in the classification situation, mean squared error actually doesn't make any sense because we're either right or we are wrong. So it's a binary decision, so there is no continuous uncertainty here. So for classification, we'll use a different metric called a Gini. And the lower Gini is better, the higher Gini is worse. So 0.6 is a very high Gini coefficient, also called Gini impurity. And Gini of 0 means that it's a pure data set. In this case, there is only one class and nothing else is present here. So it's a very good, good split. And the tree train algorithm is trying to minimize this Gini at every split. In that way, the algorithm is very similar to regression, where we try to minimize mean squared error, and here we're trying to minimize a different metric called Gini. But other than that, Gini impurity. But other than that, the algorithm is extremely simple. And in fact, in a moment, I'll show you how to do this split by hand using Excel, similar to what we've done with the regression, but for this very data set and using classification.